Hello and welcome everyone to a presentation about neural networks. I will be your host. My name is Vytenis Urbonavičius and I'm working in Wix events team as a front-end engineer. Now in Wix we have like a dedicated team of data science which concentrates on topics such as artificial intelligence, neural networks. They are making decisions based on limited data. They are enhancing images where there is not enough pixel information. They are like analyzing natural language, improving our bots, and so on and so forth. Now, however, we as conventional backend or front-end engineers, at some point in time, this subject may also creep into our development lives, and I think it is essential for us to understand how neural networks work, what they can be used for, how they are trained, at least at a basic level. So this is what this presentation is going to be about. The duration of this presentation is expected to be a little bit more, maybe than an hour and 15 minutes. And you are not expected to know anything in advance about neural networks in order to understand what I will be talking about. So even if you haven't seen any prior presentations, even those which were made inside Wix, you should not be in any trouble. Now the goal of this presentation is so that when it finishes, you should feel empowered to start experimenting on your own and continue learning about neural networks if you wish to do so, and without necessarily having to listen to like 20 hours of lectures about theory just to get started. And it is like a kickstart presentation to help you kickstart the journey on neural networks. However, even though it is a kickstart presentation, you should still expect it to contain quite a lot of info, and therefore buckle up and be prepared. We will start from very basic stuff such as vocabulary, some basic terms, some basic ideas, and then I will explain what a neuron is, what a neural network is. I will talk about how neural networks can be trained, how those neurons can be connected together. We'll give some examples of potential neural network architectures. And in the very end of the presentation, I will spend some time and give you a couple of very basic examples I did myself when I was learning neural networks. So even though that's not going to be anything complicated, I hope it will be interesting. Now, quick disclaimer, I myself am relatively new to the subject. So this presentation is a result of my guild week, meaning that Wix actually allowed me to dedicate 2 full weeks just learning about neural networks, experimenting with them, setting up environments, doing various stuff. And I believe I really learned a lot during this time. So I will be really happy if I manage to share at least some of that information with you today. So wish me luck, hold my beer, and let's get going. So as I said, let's start with some really basic theory. And in the initial slide before, I gave some metaphors related to flying to airports. So now let's take another type of transportation to help us with vocabulary. Let's talk about cars a little. So when you are describing some type of objects, such as cars, you can choose different ways to describe those objects. So for example, about cars, you could say what engine size the car has, what color it is, what rim size it has, and probably you could say many more things to describe a car. Each separate data item like that is going to be called a feature. And when we will choose a set of features and provide a full description of a car, that full description is going to be called a feature vector. Now, most of us have some experience with cars already. So given this full feature vector, we might be able to draw some conclusions from that. So for example, we might be able to say that an older version of Lexus GS is likely to cost about 4,000 to 8,000 euros in the market. And the way we make this kind of conclusion is called a model. So what is a model? A model is, it could be some type of function which allows us to come up with the result. It could be a set of rules, or in the context of this presentation, it could be a black box implemented using algorithm of neural networks. And if that's the case, this model would also be capable of learning. So you could give examples from real life, actual cars and their prices. So it would learn to make conclusions about car prices even better. So if you are using this model, to make those conclusions. Those conclusions are going to be called predictions. And if you're taking those actual prices from real life and giving them to the model in order to improve it, then those conclusions, those outcomes are going to be called target vectors. So if there is more than one number provided as an output, it's going to be a vector, more than one output. Or it can be called in general like target, something that you want your model to be able to predict. Okay, so now we have established the fact that some implementations of models are capable of learning by providing them examples from real life. So what are those examples? So they are basically combinations of inputs and outputs, or feature vectors and target vectors in our new vocabulary. So a single example like that is going to be called a data sample. And if we take all of the data samples that we have together they are going to be called a data set. So, okay. So this way of training a model by providing it a data set from real surrounding world is called supervised training. So this is pretty much the way we used to train ourselves, because we are also like neural networks, biological ones in the brain. So let's say in school, the teacher at some point told us that things like 2 + 2 is 4, 5 + 5 is 10. And then after some time, we were able to generalize to understand the problem of addition, and we were able to decide by ourselves that 100 + 100 is 200, even though our teacher may have never told us that explicitly. So this is how a supervised training of those models work. There are other training types. So there is another type called unsupervised. So this is when you have no teacher, you are given a lot of data. You may not even realize what that data is about, but you try to look into those numbers really, really hard, and you try to find some patterns. You try to find some correlations, and you sort that data in some way, or classify into categories, so that when the new data comes, you will be able to put it into the correct category based on prior experience. So this is called unsupervised training. And then there is another type of training, which I find to be the most fun one, which is called reinforcement training. So imagine you are the model which is going to be trained this way. So let's say you have never driven a car before, and you are given a brand new car, given the keys, and you are told just sit and drive. However, you manage to do that. So you sit into the car, by some miracle you find out that you need to twist the key or press the button to start the engine, and you start going. You drive the first 100 meters only to realize that you have no idea how to steer the machine. So you actually accidentally go sideways and crash into the wall. And then there is a person standing next to the road looking at you, and he says, okay, I see that you managed to drive 100 meters, so I will award you a single point for that. But I'm rich, so I'll also give you a new car, so you can sit into that new car and try again. So you take this new car, sit into it, and then you think you should probably do something differently this time in order not to crash, hopefully. But you have no teacher, so you have no way of knowing what is the right way of driving a car. So you decide to do some things differently in a random way. So you start the engine again, you start going, and you crash into the wall again, but this time you managed to go 200 meters. And the person standing next to the road looks at you again and says, okay, now you drove 200 meters, so I'll award you with 2 points for that. And since 2 points is more than 1 point, which I gave you before, probably you should drive your car more like you did on the second time. And less like you did the first time. So this evolutional way of training is called reinforcement training. And the cool part about it is that in this way, models are able to learn without being given explicitly the data set to learn from. So they kind of generate that data set by interacting with reality automatically. And in this way, models are capable of learning all by themselves to a large extent. Okay. So now at this point we kind of know that there is an abstract stuff called a model. In some cases we can train it, and there are different ways to train it, but how actually can it be implemented? And one way to implement that model is a neural network. I'm going to concentrate on artificial neural networks on our presentation. And I gave a lot of thought actually how to describe neural networks in case you didn't have prior experience working with them, or only maybe knew the name and didn't know what hides under that name. And this is what I came up with. So the first thing you need to realize is that everything around us can be described in functions. So whether it is light, whether it is sound, whether it could be like amount of bugs you make per hour in your code, all of those things are functions. In some cases, or in many cases, those functions may be really, really complicated. They may have a lot of variables, and essentially they are unknown to you. So you cannot actually know the underlying function, but you just see the results of it. But what you can do is you can experiment with reality, you can experiment with that function, and you can see what happens when you perform those experiments. So you can collect data samples from reality. And let's say those data samples are provided to you in some form of numbers. You can plot those numbers into the graph like I did on the slide. And then somebody gives you a bunch of sticks and asks you to put those sticks on another plot in such a way that those sticks would kind of cover as many dots from the data samples as you can. So you come up with some kind of approximation for the hidden function by accident by just connecting those dots together. And even though you have never seen the hidden function before. And this turns out to be exactly what a neural network does. So the one and only purpose of a neural network is to approximate functions. And it may sound limited at first, but when you think that functions is basically everything can be described in them, then you realize that neural networks are pretty powerful. And when looking into this simplified example, you could imagine that a single stick is represented by a single neuron. So the more neurons you have, the more sticks you get. So the more sticks you get, the more complicated functions you can approximate. And on the other hand, the more samples you collect from reality, the more accurately you can place those sticks on the plot. So again, your approximation will become better as a result. So this is how it all works on the very simplified way. Now let's bring this simplified example a little bit closer to how it looks in real life. So let's say we have some function. Now this function is equals to 0 when x or horizontal axis is below 0. So it's represented by the dotted line. And the function starts going upwards at some angle after x becomes positive. And then we have another function which is very similar, but it has a slightly different angle and it bends at a slightly different place. So what we choose to do with those two functions is we sum them together, and as a result we get a third function which is more complicated than the first two, because now it bends in two different places. And this simple example actually represents rather accurately how a neural network operates, because the first two functions on the top represent two neurons. A neuron is nothing else than a function. And all that the whole neural network does on the basic level is that it takes all of those neuron functions and sums them together to get the final approximation function which you are trying to use to explain something that you're trying to analyze. So this is quite a good explanation of how neural network works on a basic level. And one more thing you can draw from this slide is that those neuron functions at the top, they have a bend at a certain place. So those are not straight lines from minus infinity to plus infinity. They have a bend at a certain place. And the reason for that is, if neurons were completely straight lines, if you would add them together, you would only be able to get another straight line as a result. And if your neural network would only be capable of generating straight line approximations, it wouldn't be actually very useful. It wouldn't be able to approximate any complicated stuff you are trying to analyze. So this is why neuron functions are non-linear. They have some curves and bends in them. Okay, so now let's take this explanation and connect it to the previous explanation with sticks. So in real life, those sticks which I showed you initially, they look a little bit differently. They look more like this. So here we have like 6 neurons. Each of those neurons is represented by a single line. And this line is actually infinite. It extends to infinity. I just couldn't draw it outside of the slide. And when this line reaches the 0 on the vertical axis, it continues just always at 0, so it flattens out. So there is a bend in each of those lines. And when you sum those lines together, you would still get the same kind of approximation I showed you in the initial example. So this is how it works. And when you get a brand new network, which hasn't seen data before, those lines on the left side, they would be at random positions, at random angles. And when the neural network would be training, what would be happening is those lines would be moving around, the angles would be changing up until their sum would become a good enough approximation for you to use. So this is actually already quite accurate representation of how neural network works, except that, well, this representation has one limitation. It represents a neural network which only has a single input. In real life, more often than not, you would have neural networks operating based on multiple inputs, and this suddenly becomes multidimensional problem. So you cannot just put it into slide like that easily, but the example I showed you should be relatively good for visualizing what is happening under the hood to understand how neural networks operate. Okay, so now we kind of looked into the overall network behavior, what is happening in those neural networks. Now let's dig a little bit deeper into how a single neuron works. So this is a very common representation of how data flows through the neuron function. Remember, neuron is nothing else. It is just a function. So on the left side, we have inputs, x1, x2, x towards xm, and each of those inputs is nothing else, just a simple number. On the right side, and those inputs may be coming like as input for the whole problem that you are trying to solve, or those inputs would be result of other neurons, and they would be then passed on to this neuron to continue calculating upon those values. On the right side, we have a single output, so every neuron function outputs just a single number as a result, and that's the product of what neuron produces. Then, if we look back to the left side, next to each of the inputs, there is a W value. And this is like a multiplier for each of the inputs, or coefficient. And it's called weight. So the weights are being changed when neuron is learning. The purpose of weights is to signify how important each of the inputs are for the final outcome of the neuron. So if, for example, x1 would turn out to be not important for the final outcome during the learning process, corresponding W1 coefficient would become close to 0. So x1 would then be multiplied to something close to 0, and the final product of that would be 0 or close to 0. And when you would sum this value with other values, it would not impact the calculation too much. On the contrary, if you would have some number which is important in the input, the corresponding weight would become very much negative or very much positive. Now, if we have a neuron which only has one input, so I did show you this representation of neuron as a line with a bend before. So in this case, if you would be changing the weight of that single input, you would be actually changing the angle of the line. So this is what weight does to the output of the neuron. Then, if you look at the top of this representation, there is another additional input called a bias. So the purpose of bias is to move the function around a little bit. You do not want all your neuron functions to bend exactly at the same place, because when you sum them together, you want to get some complicated function which is like bending back and forth to represent some phenomenon that you are analyzing. So you need to be able to move the function around a little bit. And this is done by changing the weight next to the bias. Then what you do next is you take all of those inputs multiplied by their corresponding weights, and you add them together. And at this point, if you think about the neuron, up to this sum, you take some values, you multiply by weights, you sum them together. So what you get is nothing else than a formula for a straight line. And what I did say before is it's not very useful to have a neuron which only is capable of producing straight lines. So we need to somehow introduce some curves and bends into it. And this is why the output of this sum is then taken and provided as input for some nonlinear function. So we are trying to like take this line and bend it or curve it in some way. And there are like infinite amount of activation functions which could be used for that. But the main purpose of this function is to just introduce some nonlinearity, some kind of curves into that line function which we produced using the sum. Now, activation function is like a parameter which you specify when you are defining the network. It doesn't change afterwards, because if you would change it for neurons, you would need to retrain the whole network, because the behavior of neurons would change. And so you select it, perform the training, see how it performs. If you want to change it, then you need to retrain the whole network all over again. And if we look back into the line with the bend representation of a neuron, so changing activation function would change the shape of this whole line. So it would no longer be a line with a bend, it would be something else. So this is how it works. And in fact, this line with a bend, which I'm constantly talking about, is one of the activation functions called ReLU. Some other examples, I can just show them on the screen. So there are really many of them. These are some of the most frequently used ones. So the best activation functions are those which mimic the curves and bends of the hidden function the closest. But the problem is that by definition, hidden function is not known to us. So we cannot always be able to choose the best activation function just like that. We might need to do some experimentation to actually see which one of them performs best. And yeah, I mean, designing neural networks sometimes requires this kind of experimentation. You may find some articles which describe which of those functions need to be used for some known problems, such as image recognition or some stuff like that. But if you are solving a new problem, you will probably need to do some experimentation. Okay. So at this point, we already gained a little bit deeper understanding how neural networks behave. And we can proceed to talking about how we can train those neural networks. How can we actually manipulate the weights to perform something meaningful? But the first thing, especially if we use the supervised training method, the first thing is to have a lot of data for training. So we need to collect a lot of data to be able to provide to the neural network to train it. But it's not enough. We can't just take this data and pass it to the neural network to learn from. We need to prepare it in some way. So the first step, what we need to do is we need to normalize the data. What do I mean by normalizing? And I'll explain by example. So let's say we are describing our cars again. And we have two different inputs for the neural network. One of them is in kilometers per hour. Another one is in kilograms, because we are defining the car's weight. The kilometers per hour can extend from 0 to, 400 kilometers per hour. When we are talking about weight, it could be from 0 to, something like 4,000 kilograms or whatever. And the thing is that those are completely different scales. And neural networks, when they operate, at some point within the neural network, it will be adding those values up together. And it will be more difficult for a neural network to come up with something meaningful if those scales of those two different numbers are different. So it's better to change those numbers, to scale them down into the same scale. So for example, you could squash those values between 0 and 1. So 0 kilograms would correspond to 0, and 5,000, or the maximum which we chose to be the maximum of kilograms, would become 1. All values in between would be proportionally squashed between 0 and 1. And we can do that for all of the inputs and match also the format on the output side. That's ideal. In that case, neural network is likely to perform better. Also, it is a good idea to provide inputs for the neural networks in as flat way as possible, meaning that the same input should always mean the same thing. So you shouldn't, the meaning of the input should not depend on the value on another input. So you should flatten the inputs to represent one thing at a time as much as possible. So it's a little bit similar problem to when you're normalizing a database or something like that. But that's not enough. So now we kind of normalize the data in this way, but that's not enough. We need to do one more step. So we need to balance the data out. and I'll explain that in another example. So let's say we have a neural network which is designed to distinguish images of cats from images of dogs. When we are training this network, if we would provide 1,000 examples of dogs versus 100 examples of cats, what we would get is that our network would start to cheat a little bit. It would become biased. It would learn, instead of learning to distinguish cats from dogs, it would learn that there are many more dogs in the world than there are cats. So it would be less afraid to make a mistake if it would call a cat as if it was a dog. So it's not what we want. So to avoid this kind of situation, we need to balance the data so we would be providing the same amount of examples of cats and dogs. If we don't have enough examples, we can use a technique called oversampling. So we can take all of the data samples that we have and we can use it more than once, as if we had more data, twice or 3 times more data. So this is the trick. So once we have balanced the data out, so we have now kind of prepared data set, that's not all. We need to do one more step. So we need to split this data set into several parts. The first part is going to be called a training data set. It's the biggest one, and it would be used directly for modifying the weights of the neural network. Then we would need another data set which would be much smaller, maybe 20% of the size, which would consist data samples that our neural network has never seen before. And we would use this validation data set to check whether our neural network is capable of performing on unseen or new data, and whether it actually manages to generalize the problem and understand how things work, as opposed to memorizing inputs and outputs, which is something we don't want to achieve. And when we use validation data set, we can use it to determine when we need to stop the training process. And also we can use it to tweak some training parameters along the way. So it does participate in the training process, but not by directly manipulating the weights. But then we need a third data set. Again, it's one of the smaller data sets. When we finish the training process, we need to know how good our model actually is, whether we can actually use it in real life. So we need another data set of data that has not been seen by our neural network, and not just not seen, but the data set which has not participated in training neural network in any way. So we call it a testing data set, and it's used solely to evaluate the final results. So this is the 3 parts which we need to proceed with the training. So at this point, we already have our inputs, we already have our data, we can proceed with the training itself. Now, fortunately, the training process from the algorithmic perspective is mostly done by some software, such as TensorFlow. So we usually just call a function called fit or whatever, and it kind of adjusts weights for us. But in order to understand what parameters we would give to this function and how to configure the whole process, we need to understand a little bit what is happening inside this function. So what this software would essentially be doing during the training, first it would be asking our model, even if it's not trained at all yet, it would be asking to predict results based on some data sample from the training data set. Then it would compare this prediction, which would be complete nonsense at first, to the target vector, what was expected. And it would calculate the difference between those two. And it would calculate something called loss. So loss it's not actually correct to call loss a difference between expected and the actual result, because loss could be calculated also by taking a square of that value. So it would be L2 loss. Or you could use some more sophisticated ways to calculate loss. So it's better to think about loss as a cost function for making a mistake. It's a cost for mistake for our network. Now, once that is done, the software would perform a process which is called back propagation. So it would be going through all of the neurons in our neural network. It would be going through all of the weights within those neurons, and it would be trying to adjust them to decrease the loss. So it is possible to mathematically calculate dependency whether for each of the weights, whether it needs to be increased or decreased in order to reduce the loss function. And our main goal is to reduce this loss function as much as we can. So basically, mathematically, we can calculate like a gradient, the dependency between weights and loss function. So it's depicted on the right side of the slide. And it can be like huge mountains with deep valleys, and we would be trying to find our path through this very complicated landscape. Of course, again, in reality, we would have more than 2 weights. We would have many weights, thousands sometimes. So it, again, wouldn't be possible to depict it in 3D like I did here. But to imagine what we are doing is basically we are trying to go down from the mountain to the deepest valley. And this process is called gradient descent. Now, the problem with gradient descent is that even though we do know which way we need to go, we don't know how far we need to go. We don't know by how much we need to change those weights. Or in other words, to say the same thing, we do not know the learning rate. We do not know how much we need to change the weight in order to get to the minimum of the loss function. So this is the reason why training is not performed in a single iteration. It needs to be performed in multiple iterations over and over again until we get a good enough result for us to use. So once we perform this backpropagation, we modify the weights. Then what we do is we validate our updated model. So we use validation data set and then decide whether we need to continue training, or perhaps we need to change some parameters, maybe the learning rates themselves, and then decide what to do next. So this is how the training works. And I already indicated one of many challenges related to training. So I indicated that we do not know the learning rate. So let me just dig a little bit deeper into that. So what happens if our learning rate is too high? So imagine those mountains and those valleys and the gradient. So if we are jumping in big steps, we may accidentally jump over the lowest point in the gradient, which we don't want to do. So that's one thing. If our learning rate is too small, on one hand we would be learning slowly, but also we can accidentally get stuck in a local minimum. And it's pretty much like if we think about how Newton understood gravity. So he got stuck in a local minimum of our reality. He thought that he understood how gravity works. But then Einstein came and explained us how it may work in a more sophisticated way. And maybe he's not even the best. Maybe he doesn't even have the best explanation. Perhaps in the future we will find out that there are more things at play here. So we don't want to get stuck at that local minimum as much as we can. How to deal with that? So one way is to juggle with learning rates and change them back and forth. We could do that manually, but usually we don't want to do it manually. Usually we would use some of the algorithm already provided to us by the software such as TensorFlow. We would use something called adaptive learning rates or optimization algorithms, which are actually changing those learning rates automatically for us. And in some cases, they would be even changing the learning rate for each of the weights individually in some cases. So this is one of the challenges and how this challenge is met using the software at our hands. I'll give you another example of training challenges. So how do we know how much do we actually need to train the network? What happens if we train it too little? So it's pretty much like when a student has a book of theory for the lecture, but he doesn't read it or doesn't read it enough. So he wouldn't be able to understand what's in the book. He wouldn't be able to understand the main idea or the theory behind it. So this situation is called underfitting. So either we need to learn more and perform more iterations of training, or we need more neurons. We need a bigger brain, so to speak, or more sophisticated, more complicated connections between those neurons to achieve a better result. So this is one part of the problem called underfitting. So if we learn enough, we would be able to generalize the problem, and this is what we want to achieve. But then, on the other hand, if we learn too much, we would have another problem called overfitting. So instead of generalizing the idea, we would start memorizing inputs and outputs by accident. So we are trying to learn data so hard that instead of understanding why the data is looking like that, we would just remember by heart the inputs and outputs. This is not what we want to achieve. How to deal with that? So there are a couple of ways. One way is to monitor how model performs based on validation data set, and we can choose to stop learning when we see that neural network starts to misbehave based on unseen data. And the other thing which is sometimes used is something called dropout layers. So it's like drinking alcohol. So essentially you kind of disable some of your neurons in the brain randomly during the training process. As a result, you are learning slower, but you are forcing different parts of the brain to perform the same task in different ways. And in some cases, it showed that this helps neural network to generalize the problem a little bit better and to understand what is happening in the hidden function. So this is another example of the challenges during training. Okay, so there are many more challenges. I will not be able to go through all of them in this presentation because it's just too many and too little time for that. But what I want to take out of this slide is that training of neural networks is a little bit creative process. So do not expect to succeed on your first attempt, because usually you will need to tweak the network, you will need to do some experiments. And there are, of course, articles, various like scientific articles to help you out, which deal with common problems, with common solutions. But there is always a chance that another person will come and find a better way to do things. So this is an evolving science. This is a new science relatively. Things change all the time. So expect a little bit of required experimentation if you deal with neural networks. All right. So we talked about how neural networks work. We talked about how we can train them, but we haven't talked yet how to actually take those neurons and connect them together. How do we actually create a network? And in theory, we could connect neurons in any way imaginable. We could connect them in such a way that connections would look like roads between cities on Google Maps. And there are use cases where these kind of connections actually make sense. But there is another quite common approach how to organize neurons, is to organize them in layers. So neurons within the same layer are not connected to each other, but layers are connected but there are connections between layers in some way. And if it happens so that every neuron in one layer is connected to every neuron in another layer, in such case, these layers are gonna be called dense layers. So in the layered architecture, normally what we would have is we would have an input layer. So those would be neurons accepting initial numbers, inputs for the problem that you are trying to solve. And in the last layer will be called output layer. So you would have as many neurons as there are outputs to the problem. So as many neurons as there are numbers in your prediction which you are trying to provide. Now, between input and output, you can choose to have one or more hidden layers. And the reason why they are called hidden is not because you cannot see what is inside them. You can actually explore what kind of values are going through those layers if you really want to. It's not quantum computing or something. But even if you see those values, you might not be able to understand what those values actually mean, because if you're summing scaled kilograms with scaled kilometers per hour, what does that number actually mean? So it's difficult to understand sometimes what is happening in the middle. It's like a black box somewhat. So this is why it's called hidden layers. And also the theory goes that if you had if you had even single layer with infinite amount of neurons, and you had infinite amount of time to train those neurons, in theory you could approximate any function out there. But the reality is not very good with infinities, and this is why we actually use different architectures, different ways of connecting neurons to speed up the training process and to make those neural networks specialized for solving specific problems. So this combination of dense layers is very often used. Sometimes it's part of a more complicated architecture. Sometimes for simpler problems it could be used just like it is depicted here. It depends. But basically we are designing specialized networks for specific problems. And it is no wonder that our own biological brain, which is also a neural network, just not the artificial one, also has like segments of brain which are responsible for different tasks. So, for example, cognition, vision, speech, etc. And this is very similar to what we are trying to do with artificial neural networks. And some of the concepts even are very similar. Speaking of those concepts, so for example, one thing that we have in our brain and we also have in artificial neural networks is attention. So when we deal with data, and this is a rather common problem, is that our input data consists not only of meaningful information, but also it has a lot of noise. So it doesn't sometimes help to analyze all of the data at once. Sometimes it's beneficial to first try to separate the noise from the data which actually gives us some information, and only then proceed with analyzing that important information. So you can actually train neural networks in parts. So you can have a neural network which is capable of separating, querying the data and extracting the meaningful data out of the overall input. And then it would give it higher weights, so to speak. And then you can have another part of the neural network trained separately, which takes that data and makes the final classification or whatever problem we are trying to solve. So this is called attention. This is something we also have in our brain. Another thing we also have in our brain is called memory. So we can achieve that with neural networks as well. We can introduce that concept there. So one problem with layered architecture in neural networks is that we have fixed size of inputs and outputs. And in reality, we often need variable length inputs and outputs. And also sometimes we are analyzing functions which are varying in time. So to deal with those problems, there is a concept called RNNs, so recurring neural networks. How they work is basically you take a neural network, and when you run it once, you take its output stored in memory, in computer memory somewhere, and the next time the neural network is invoked, you take that memory and you pass it to the neural network as part of additional input. So you can run the same neural network for multiple iterations. So for example, when you are analyzing text, so it's not just important to analyze a single letter or a single word. You want to analyze that word in the context of what was said previously. So that could be achieved using some sort of memory solution. Now, this particular concept, which I showed on the screen right now, it has some drawbacks. So, for example, this simplest implementation actually is just a short-term memory, because things that happened longer ago get kind of diluted in time, and after like 6 or 7 steps, they may not be taken into account as much as you may want to have them taken into account. So there are like more complicated solutions which deal with these problems and make memory more lasting, etc. Another problem is that when you train such a network and when you perform backpropagation, you need to perform that backpropagation not only through all of the neurons and all of their corresponding weights, but you also need to do that through all of the iterations in time, as many times as the neural network has been invoked. So the training process is also quite slow. But as I said, this is just the simplest example of the concept. There are more sophisticated ideas extending this concept. Now, I would like to give you another example, but this time maybe something that I did not recognize that we have in our brain. Maybe we do. I'm not sure if it works the same way. So it's just an interesting idea of how we can use neural networks called autoencoders. So let's say we have a layered architecture, and each of the layers within the network contain less and less neurons up to a certain point. And then from that bottleneck point in the middle, we have each of the further layers have more and more neurons again up to the output. So then we train such a network in a way that we provide feature and target vectors which are equal to each other. So we ask the network to produce output which would be equal to the input. If we succeed, so the challenge that the neural network has in this case is that it cannot pass information through the bottleneck in the middle as is, because it's just not enough neurons in the middle. in order to pass the information through the bottleneck, it essentially needs to somehow extract the meaning of that data. So in this case, it could extract that this is a letter A in some way. And if we manage to train a network like this and it starts producing similar outputs to inputs, what we can do then is we can split the network in half, and we can use it for data compression of some sort. Or we could modify a network slightly and we can use it for generating data. So if we provide some noise into that middle section, the network would think that it's something meaningful and it would try to generate something meaningful out of it, maybe some image, maybe something. So it's quite an interesting concept, and it can be built upon. So since I started talking about images a little, I would like to share with you and describe another concept, which is probably the most complex one during this presentation before ending with the theory. And the reason why I want to explain it is because I use it in one of my experiments, and it's called computer vision. So how do computers actually see images, or how do they see something visual? And in order to do that, first of all, I need to explain an algorithm which is called convolution. So convolution is an algorithm which allows, for example, such programs as Photoshop to filter images, like add a blur to the image or sharpen them or do some edge detection or whatever. So this is one of the ways how that can be achieved. And the way convolution works is we take the original image. Now, image consists of multiple pixels. So each of the pixels can be described with numbers. If there is only one color, if it's black and white picture, then it means that it can be described only with one integer. So we take this data, we choose one pixel together with its surrounding pixels, with its context, and we apply some calculation on those pixels. Now, the rules, the calculations which we need to apply, are defined in something called kernel or filter. They are defined in the form of a matrix. And it's best to explain how this matrix behaves is by example. So this particular matrix you see on the screen says that we need to take the top left pixel, multiply by 1. We need to take the bottom right pixel in the highlighted area, multiply by -1, and then we need to ignore all other pixels because they need to be multiplied by 0. When we do that, we take all of the resulting numbers and sum them together. This is going to be our pixel in the filtered image, in the same location as the original pixel we were analyzing. So, and then what we do is we repeat this operation over and over again for every single pixel on the original image. So this is the process which is called convolution. And if you open some open source image editing software such as GIMP, you would see that there is even a feature called convolution matrix, where you can define that matrix manually. And by default, the default matrix only contains 1 in the middle and zeros everywhere else. So default matrix doesn't actually change the image. So it only multiplies the original pixel by 1, which doesn't change it in any way. But you can define your own matrix to do something more sophisticated. So for example, if you would specify at the top, you would specify 1. At the bottom, you would specify -1. You would get something close to edge detection. So if color at the top would be the same as color at the bottom, they would cancel each other out when they are summed up afterwards. But if the colors differ, you would then get a result of very much positive or very much negative value. So then you would take an absolute of that value, and you could make the corresponding pixel very much light. So you can do an edge detection, which looks pretty much like this. Okay, so this is convolution, and but this I haven't yet described it in the context of neural networks. So the trick is, what if instead of defining this kernel manually, what if we replace those numbers in the middle with neurons? And we would give some training data to our neural network, and we would ask neural network to come up with some filter which would highlight meaningful information for the neural network to achieve the target vectors which we are using, which we are asking for. So we would place neurons in the kernel, and we would basically ask the neural network during the training process to invent filters for us instead of us defining those filters. So this is the key idea behind computer vision. So now let's have a look at the full algorithm of computer vision, how it usually looks like. So let's say we have, I don't know, some team consisting of up to few, I don't know, 6 or whatever amount of people. And we want our neural network to recognize which person is depicted from this known team in the picture. So we give this picture to the neural network. Neural network would then apply convolution on this picture, but it would apply it not once, but it would apply it multiple times with different filters. And initially those filters would not produce any meaningful data, but as the neural network learns, it would start extracting and highlighting features within this picture which are important in order to achieve the result, in order to recognize the person. So once we perform this convolution and something gets highlighted, we would shrink those images, make them smaller, so it would be easier to analyze those pictures further, and we would also be analyzing the largest part of those pictures going forward. So we shrink those filtered images, and we would apply convolution on them again, getting even more resulting pictures as a result of that additional convolution process. And then we would shrink them even more and perform another convolution. So we would repeat the process several times. This shrinking is called polling. So essentially, we just reduce the amount of pixels based on some rule. For example, the maximum, the brightest pixel out of 4 or whatever. So this part, what it does, it basically tries to detect features in the image. And at first, we try to detect low-level features. Then when we shrink the images and start analyzing larger areas of those images using further filters, we detect higher level features. So I'll show that in the next slide as example how those features could look like. And in the end, what we come up with after this process, we get a large number of very small images where each of those images contains some kind of meaningful information about some feature on the photo, on the original photo. And then we can just flatten that information, those pixels, into a single line, because that's how input for the neural network looks like, usually. And we could feed this list of numbers to a few dense layers to make the final decision, for example, to recognize a particular person which is shown in the picture. So this part is called classification. Now, how do those filters actually look like when we perform this whole operation? So this is pretty much like an illustration of what neural network could come up with when it's designing filters during the training process. So initially, when it works on the overall image, it's likely to start highlighting dark spots, light spots, edges, etc., some low-level features. When it shrinks the image and starts applying filters on larger part of that image already pre-filtered, it may try to distinguish some facial features such as noses, eyes, or whatever. And finally, when it shrinks it even further, it would try to highlight even higher level features of some sort. So this is how the analysis happens. And those filters, remember, they are not hard-coded. They are invented by the neural network when it was learning based on the data we provided to the network during the training process. So this is how the computer vision works. Now the power in this is that this algorithm can be used not only for vision, it can be used also for sound, because sound can be depicted visually as spectrogram. It could be used for games, because you could take some, for example, strategy game, and you can depict situation on the map as a picture. So in fact, this algorithm is more universal than it seems at first, and it's quite powerful. Okay, so this was the hardest kind of concept I wanted to explain, and I think at this point enough with the theory. Let's have a look at my own bloopers, what I did when I was experimenting with neural networks. So I decided, since I did mention that I am a front-end engineer, not a back-end engineer, so I know JavaScript language best. And there is a tool called TensorFlow allowing to work with neural networks. It's originally designed for, I think, if I'm not mistaken, for Python. but it's being ported to JavaScript, so I can write JavaScript code in order to train the model to use the neural network. So this is what my examples will be based on, but there is no complex code, so it should not be very difficult to understand what is going on. So the first question for those who are trying to use TensorFlow is usually what is a tensor? So I just want to clear this thing out once and for all very quickly. So tensor is a mathematical term, but from the development perspective, you could just treat it as a multidimensional matrix. So imagine it's just a data type. It's the data type which is understood by the TensorFlow software. And if you have a multidimensional matrix, you can convert it into tensor. And if you have a tensor, you can convert it back into multidimensional matrix of multidimensional arrays in JavaScript, for example. So this is the first thing. I just quickly wanted to clear things and not get back to this going forward. So now going into my examples. So I was thinking, so the common way of how neural networks are used is you think of a problem which you need to solve, you collect a lot of data to train the neural network, you design its architecture, you spend a lot of time tuning that architecture, and you train the network. And once that hard work is done, you already have a model which is pre-trained, and you can deploy it somewhere. So you no longer need to train it. You can just deploy and query it to predict some results based on prior training. So the training process can be CPU, GPU intensive stuff. But when you deploy it, when it's already trained, it's pretty straightforward usage. So it doesn't require a lot of resources to do that. So my initial thought was that I want to solve some super simple problem. I wanted to make sure that I can write a working algorithm, and I wanted to be able to deploy it somewhere. Since I'm a front-end engineer, I deploy it to a web application, but you can deploy it anywhere essentially. And the simplest problem which I could think of was basically comparison of two numbers. So my super clever neural network had to basically tell whether two numbers provided as inputs are equal to each other or not. It's not the most debated problem out there in mathematics, but still, it was a good thing to try the neural networks for the first time in my life. So this is what I did. So the first step, what I did is I defined the neural network itself. And I mean, I didn't define it in one go. I did some mistakes and tuned it up a little, but this is what I came up with eventually. So I had a layered architecture. I had input layer, which consisted of, which was accepting two integers as input. I had output layer with only one neuron, which was outputting a number, and I decided that if this number would be close to 1, it would mean that numbers are equal. If it would be close to 0, it would mean that numbers are not equal. And I chose to have two hidden layers in between, 20 neurons each with two different activation functions. So one layer has one activation function for its neurons, and another layer has a different type of activation function. And why two layers? Why two hidden layers? Why 20 neurons? Why these types of activation functions? This is the result of my experimentation. Probably you could find better configuration depending on what numbers you are manipulating with and what activation functions you use, etc. This is what I came up with, and it worked relatively well. Then, so before using this model, you would need to compile it. But before that, I just want to say that when you are training a neural network, training may happen in several steps. You don't have to train it all at once. So you can train it, you can save it, you can continue training later. You can even pre-train the network in one way and then take different kind of data and continue training network in some other way. So there is a lot of creativity involved in how to train networks in the most efficient way. So you can store the model and you can retrieve the pre-trained model to continue working on it. As I said, before working on it, you need to compile it. So there is a function .compile which is provided by TensorFlow, and you need to provide a few arguments to that function. So the first one is loss. As I said, it's like a cost for mistake for the neural network. And there are like a bunch of predefined loss functions in TensorFlow. You can choose them by just reading descriptions what they are used for. So for example, binary cross entropy loss function is used when you have a classification problem which contains only a binary output, 0 or 1, or Boolean output. So since I had this kind of problem, this is why I used this particular loss function. Then I used an optimizer. So this is the thing which allows me not to juggle with learning rates on my own. This is the algorithm which dynamically adjusts learning rates during the learning process. And I chose an algorithm called Adam. Again, there are many algorithms. You can read descriptions, how they behave. You can try them out. You see which one is working for you best in particular case, and you choose based on those criteria. And finally, I added a metric, which is just something that was printed into console, so that I would be able to observe during the training process how my accuracy of the algorithm is improving over time. Normally, you would want to plot it visually. Initially, I just was printing it out into console and observing it that way. And then I needed to generate data samples, so that I would be able to train the neural network. So I decided that my numbers would be between 0 and 1 million. I scaled them down to match the format of the output, which is 1 or 0. So I scaled them all down between 0 and 1. I squashed those numbers, so million became 1. Let's say 500,000 became 0.5, and so on. And then you can see the balancing part. So when I was generating samples, I was generating equal amount of good samples and bad samples. Good means that two numbers are equal to each other. Bad sample means that two numbers are not equal to each other. So I wanted to avoid any bias in the network in this way. Okay, so this is how I was generating data. Then I kind of converted the data into the way TensorFlow is able to understand it, into tensors. But the key part within this slide is is at the very bottom. So I generated my training and validation dataset. The training dataset contained 1,000 samples, and validation dataset contained 200 samples, which is just a lot smaller than that. Usually it is smaller. And then I started the training itself. So there is a function in TensorFlow called fit dataset, and there is another function called fit, which is a lower level function if you want more control and more manual labor. So what I did here is I provided the training and validation dataset to this function. I told it that I want to train for 1,000 iterations based on the data samples that I generated. And then I provided two callbacks. One was called early stop, so this was implemented by myself. It was monitoring how my model behaved based on validation data. And if it saw that it starts misbehaving based on unseen data, then it stopped the training process. And it didn't reach 1,000 epochs. In fact, it finished, I think, even below 100 or even lower usually. And then I had another callback which was constantly saving the model, so I could stop the training and continue it later if I wanted to. So this is the training. After the training, I could use the model like this. So I could just call predict, provide my two input numbers in the tensor format. So this is the code which was converting it into the tensor data type, which is understood by TensorFlow. And I was printing out the final result, which is number either close to 1 or close to 0. So I rounded that number, and this is how I made a prediction whether numbers are equal or not equal. Okay, then I also used some software to plot some information visually. So ideally, you would want to plot the loss function, how it changes over time during training. In the first experiment, I plotted how my model is predicting whether numbers are equal or not. I have put my inputs on horizontal and vertical axis and placed dots where my model thought that those numbers are equal. So that's what I used it for. And yeah, I ran the training process. For this very simple problem, it was relatively fast. So it took approximately, 10, maybe 15 minutes to train it until my callback asked me to stop the training process because it was already too much. I was using my GPU. I have a setup on my home PC to use the GPU to make it faster. And this is pretty much what I expected to see after the training. So I expected to see a line like this representing So on the horizontal and vertical axis, I had my inputs, and the dots were representing numbers which were equal. So there should be like a diagonal line like this as a result. But what I saw, in fact, when I was trying it for the first time, I saw something like this. So after one epoch, after one iteration, my model was thinking that most of the numbers out there are equal to each other, which is obviously not right. When I ran it for 10 epochs, everything narrowed down and was closer to reality, but still pretty bad. After 100 epochs, it became even better, but still I could observe that for some reason, the bigger the numbers get, the wider this range of equal numbers is there based on what my model perceived as equal numbers. So eventually I realized why that is happening, and I did say that I scaled the inputs between 0 and 1. But to be fair, initially I didn't do that. And this is what happens if you do not scale your data. So your neural network starts messing up with data a little bit, and it becomes hard for a neural network to figure out how everything needs to look like. So after I scaled the data, it narrowed down and it became more close to the line which I wanted to achieve. And when I tweaked the network a little bit more, when I ran it for more iterations, I got the result I wanted. So this was kind of success, except I cheated a little. If you look into this plot carefully, you would see that numbers, the scale of numbers is really, really large. And if you would zoom into this line, you would see that it's actually quite wide. But the thing is that neural networks are designed to approximate functions. They are not designed to mimic mathematical functions exactly. So you shouldn't expect ideal results with neural networks. They are like approximations of reality. So I didn't actually work any further to reduce the width of this line. Instead, I decided to just multiply my inputs by a certain number to avoid this variance, and then pass it to the neural network to decide whether numbers are equal or not. And this is how I overcame this problem, and I just wanted to concentrate then on trying to deploy this on the website. And deployment is pretty straightforward. When you save the model, in the case of TensorFlow, you get two files. One is model.json, which contains information about what layers you have, what neurons you have, activation functions, what kind of connections are there between layers, etc. So this is like a static data for the architecture of your model. And then you have another file called weights.bin, which contains the training information, so the values of the weights. It's a binary file. And it's the usage, the deployment of such two files is pretty straightforward. So once you have these files deployed somewhere, you can just load them with, in this case, with TensorFlow. TensorFlow has a variant which is ported to the browsers. So I just loaded that model and called .predict on this model. So I was able to pass inputs and it spat out the outputs which I expected. So overcomplicated way to compare two numbers, essentially. So I was able to have a website which was comparing two numbers in this super complicated way. So this is my first experiment. I think it was relative success. But I did one more experiment, and I would like to share some information about it as well. Maybe it will be interesting. So there is a game out there which I really love. It's called Scripps. It's a game where thousands of players are coexisting in a huge world. They are controlling small units called creeps. And those creeps are capable of fighting each other. They are capable of building bases, mining minerals, trading, and so on and so forth. Those are like small countries, so to speak. And the thing about this game is that it's designed for developers. You can automate almost any aspect of the game, or maybe all of the aspects of the game completely, so you can have a fully automated bot. And so what I wanted to do is I wanted to take out a small bit of game mechanics from Scripps and try to automate it using a neural network. And the mechanic which I chose to use is battles between creeps. So I decided to simplify everything, so I ignored like buildings, I ignored many things that can happen in the game, and I provided this simplified scenario to the neural network in a similar way as an image. And I marked one creep in a special way so that it would be considered as the creep which neural network is controlling. So the responsibility of a neural network was to control only one creep on the map. The output of neural network had to be one of 16 possible cases, so either creep could move to one of 8 possible directions, or it could shoot to one of 8 possible directions. This is what I wanted to achieve. So I started with a very long shot idea. I knew that I will probably not be able to achieve it, but I wanted to see actually how much I can achieve in a very short time frame. So what I wanted to achieve, so ideally I would want a neural network which is capable of controlling battles on the game. Definitely that was too much at first, so I simplified the game mechanics. I'm starting from the end of the slide. I simplified the game mechanics, and I decided that with these simplified game mechanics I would have 2 neurobots, which I would make them fight each other, and using reinforcement training method, they would randomly change their behavior, and if that new behavior proved to be more efficient, it would be used for training, and neural networks would be improving themselves in this way, and I could just leave it for a long time and see how it goes. Now, the idea was that, but the problem was that this training method was super slow. I do have implementation for it, but it's super inefficient because emulation of the game and generation of the map was relatively slow. There are many things I would need to improve. And also, if you take completely empty, like non-trained neural networks and try to train them in reinforcement way, it's difficult because initially those creeps would be just walking in cycles or just going towards one edge of the map, and that's it. And it would take a long time until randomly they would start fighting each other. So I decided maybe it's a good idea to actually pre-train those bots using some baseline bot, which is not based on neural network. So I implemented a very simple bot, which was just charging towards the enemy and shooting at it. That's it. And then I was using this baseline bot to generate samples for the neural network, and my neural network was attempting to mimic the baseline bot. And in this way, if I managed to pre-train, then I would be able to proceed again with the reinforcement training. But even this approach, which I also have code for, even this approach was very slow, again due to some problems with efficiency of my map generation, etc. But I didn't want to spend too much time on optimizing map generation and other aspects of the algorithm. I wanted to concentrate on neural networks. So I shrank the idea even further. So what I did then is I reduced the map size drastically to make the map generation very fast. And I decided only to concentrate on a very, very simple problem at first, on shooting part, because it's much simpler than actually walking and navigating through the map, because navigation, pathfinding requires some more complicated neural networks, maybe RNNs or something like that. So I kept only very optimistic way of moving around. So probably navigation would not be working very well, but I concentrated on the shooting part. So this is what I've done, and that part I actually managed to make work. So the overall concept looked like this. So I had like 5 modules. One was trainer module, which was actually training the neural network. There was a simulator module, which was responsible for game mechanics. I could put in a scenario which I wanted to emulate. I could tell the simulator what actions I'm taking, and it would spit out what happens as a result. And they had map generator, which is actually not just a map generator, it was a situation generator. It generated a map with some creeps in it, and then asked those creeps to fight each other. Okay. And then I had 2 more modules for visualizing stuff. So one was visualizing how my neural network was learning. So I was plotting my loss function, and I could see some proof whether a neural network was learning or not. And then I had another module which was allowing me to monitor what happens if I make a couple of my bots fight each other. So this was called a map viewer. Okay, so this is an example of what maps I was able to generate. Just visual example of how those generated maps look like. And this is the concept of how my shooting part of the neural network worked. So I had a convolutional layer which was trying to analyze the map, and after this convolution there were a few dense layers trying to make a decision which way to shoot if shooting is needed. Now, I had a rough idea of how the shooting needs to work. So I imagined that if I provide the situation to the neural network in a similar form like an image, and I would mark cells of the map where I am, this is the letter O, where enemies are, letter E, and where friends are, I wanted my neural network to come up with such filters that it would be able to find situations where my creep, my controlled creep, is next to the enemy creep. And one filter could detect a situation where enemy is on the left, another filter could potentially find situation where the enemy is on the right, and in the filtered image it could highlight the cell if it matches the criteria. So this is how I imagined it could work. Alright, so afterwards, after this was done, I could pass this information to a few dense layers, and those dense layers could take those filtered images and look for those highlighted cells. And based on those highlighted cells, the final decision could be made whether creep needs to shoot left, shoot right, or whatever. So since I had a pretty good idea what needs to happen, maybe this is why it actually worked. And when I trained the network, this time it took not 10 minutes, it took a few hours, and actually I left it overnight a few times to see what happens. So after I ran the training for a long time, I plotted how loss function and how accuracy changes over time. And I saw that when I was trying to mimic my baseline bot, my neural bot was able to achieve approximately like 70% accuracy at some point, which was pretty good. And this is more or less what I expected. So this is the proof that my algorithm was actually learning something. Okay, so this is the final result on a very, very small map. Two teams, red and green, of creeps fighting each other and moving around. So this is how it looked like. Both teams controlled by pre-trained neurobots. And right, so this is the outcome of my journey so far. Maybe I will continue with this idea going forward. Okay, so this concludes my presentation so far. If you would want to see the code which I have at this moment, you could have a look at the repositories listed below. Most of the information I got for this presentation came from a training provided by MIT called Introduction to Deep Learning. So there is a link here in the slide. But even before that, I actually found one pretty nice course on YouTube actually called Machine Learning for Everybody. So there was a wonderful master's degree student who brought together various terms and various theories of machine learning. So it was very good to get the initial understanding about the terms before diving deeper into deep learning. So these are a few like sources I would recommend having a look at. And a few final thoughts before I finish. So one fun fact or Easter egg in this presentation is that if you look carefully and if you ever have a look at this presentation in the recording, you may see that a large part of illustrations used were generated using artificial intelligence. And in fact, when I was showing the computer vision slide, the person, which looks pretty realistic, in the photo is non-existent. It's completely generated. Right. And the second thought I wanted to share is that, as I said, this presentation is a result of my Guild Week. So here in Wix, we have this chance of spending time on learning stuff, on looking on how other teams work. But what I would like to encourage and emphasize is that another way of spending a Guild Week is to take some idea, something you would really like to learn and cannot dedicate time for, and align your Guild Week to be able to do that, because then it becomes really rewarding time and really interesting way of spending this Guild Week. or in my case, you could even join a couple of guild weeks together if 1 week is not enough. It's also, I think, doable and negotiable with guild masters. Okay, so that pretty much concludes my presentation. Thank you very much for listening. I hope you liked it, and all the best with your further journey if you choose to continue learning about neural networks. Thank you.